So, we have been discussing application of probabilistic methods in earthquake engineering problems. Specifically, we are focusing on problems due to vibrations caused during earthquakes, and the earthquake ground motions are modeled as stochastic processes, and we are considering how we can apply principles of random vibration analysis to these problems. So, in the previous lecture we discussed three alternative modes of representing earthquake ground motions. One is through time histories, this is basically a deterministic approach. The other through a set of response spectra. The third alternative is to represent through power spectral density function. We discussed in the previous lecture how these three alternative representations for ground motions are related to each other. For example, if we are given a time history of ground motion, we can use principles of analysis of single degree freedom systems to dynamic excitations and derive the response spectra. Similarly, if we are given a set of response spectra, it is possible to generate accelerograms which are compatible with this response spectra. This aspect I did not discuss because this is basically a deterministic it has deterministic flavor. So, we are focusing on application of probabilistic methods. So, this aspect was not discussed, but on the other hand, if we are given power spectral density functions, we can use Monte Carlo simulation methods and derive a set of time histories compatible with this power spectral density function. Similarly, if we are given time histories, we can use statistical estimation methods and estimate power spectral density function. So, these two loops are covered in this discussion in this course. Similarly, if we start with power spectral density function, we can derive the associated response spectra by using extreme value theory that is associated with probability distribution of extremes of responses using level crossing statistics and so on and so forth. Similarly, the same theory can be used to derive a compatible power spectral density if we start with a specified response spectrum. Now, one of the problem that arose when we discussed the application of response spectrum based methods to earthquake engineering problems is the problem of what is known as modal combination rules. So, to quickly recapture what the problem is, we consider a beam, a cantilever beam subjected to base motion, xg double dot of t is the earthquake induced ground acceleration, and we represent the solution in terms of we use an eigenfunction expansion and represent the solution in terms of the eigenfunctions and the natural frequencies, and we get a set of uncoupled single degree freedom systems. Now, our objective is to determine the maximum value of a desired response quantity, for example, displacement over a given duration. So, what we are interested is in determining the maximum value of this summation, the absolute value of this summation. If xg double dot of t is specified in terms of a response spectra, what we know would be essentially maximum values of response of single degree freedom systems. So, since the generalized coordinates are essentially a set of single degree freedom systems, so from the given response spectra, we would be able to deduce the maximum value of each of the values of this function a n of t. Now, the problem of modal combination arises in determining the maximum value of this absolute value of this sum in terms of the known maximum values of some of the terms inside this summation. These two terms are not equal, so there is a problem there. Now, it is obvious that the extrema of a n of t for n equal to 1, 2, 3 etc. are likely to occur at different times, because each a n of t has different natural frequency, different damping and different modal participation factor. Therefore, there is no reason to expect that all modes generalized coordinates will peak at the same time. And similarly, the maximum values may not have the same sign. For one of these generalized coordinates, the peak could be on the positive side, other could be on the negative side, and so on and so forth. The specification of response spectra do not contain information on times at which extrema occur, nor do they store the signs of these extrema. So, this information is lost Therefore, response spectra is not a complete specification, some information is lost, therefore, there will be some compromise in applying this tool. Now, moreover, if T star is the time at which this maximum value of this sum, absolute maximum of absolute value of this sum occurs, then this T star need not coincide with any of the time instants where a n of t for n equal to 1, 2, 3 reach their respective maximum values. So, there is a basic difficulty here. Now, the discussion on modal combination rules, I am using two references. The one is a paper by Dr. Corrigan, which appeared in Earthquake Engineering and Structural Dynamics. The other one is a review paper which appeared in ISCT Journal of Earthquake Technology. Now, we will discuss now the application of principles of random vibration analysis in deriving modal combination rule. Now, let us consider a multi-degree of freedom system subject to a single component of earthquake ground acceleration. Now, let us consider a generic response quantity R of t and consider the modal representation R of t is psi I S I of t from I equal to 1 to capital N. Now, R of t could be displacement, stresses, reaction transfer or any other function which is actually taken to be a linear function of the system states. The psi I is the ith mode participation factor associated with the response quantity R of t, and SI of t is the contribution to R of t from the ith mode, that is actually psi I into SI will be the contribution to R of t from the ith mode. Now, let us model the ground acceleration to be a stationary random process with 0 mean, and we will also assume that later that it is a Gaussian random process, and let us consider the response R of t in steady state. Now, we consider the one sided power spectral density function of R of t given by gr of omega. This you can obtain in terms of the transfer function of the ith generalized coordinate, and gf of omega is the power spectral density function of the earthquake ground acceleration. Hj of omega is the transfer function for the jth generalized coordinate. Now, if you recall, the extremes of response R of t are characterized in terms of moments of the power spectral density function. So, let us now write the expression for the mth moment of the power spectral density gr of omega, and that can be written in this form, and if we utilize now the representation for gr of omega in terms of participation factor and transfer functions of the generalized coordinates, we get this expression. Now, if lambda m, which is a mth order spectral moment of the response quantity, can be expressed in terms of mth order spectral moment of generalized coordinates I and j, because they appear in pair here. So, lambda m I j is this integral. Now, what we do is we normalize this lambda m I j as shown here. We divide lambda m I j by square root of lambda m I I and lambda m j j, and in terms of this normalized quantity, the mth spectral moment can be expressed in this form. Now, if m equal to 0, it is nothing but the area under the power spectral density function, which is nothing but the variance of the response process. Similarly, the second moment is the variance of the derivative process in the steady state. Similarly, lambda 0 I is actually the variance of the ith generalized coordinate in steady state. Lambda 2 I is the variance of the time derivative of the ith generalized coordinate in steady state. Now, we can associated with m equal to 0 and 2, we can define now lambda rho 0 I j as lambda 0 I j divided by this square root, and if we now interpret these moments in terms of the associated variances and cross variances, you can convince yourself that this rho 0 I j is nothing but the cross correlation between S I of t and S j of t. Similarly, rho 2 I j is the cross correlation between S I dot and S j dot. This I j indicate the indices applied on the generalized coordinates. Now, if we simplify the problem by assuming that gf of omega is a white noise, in which case power spectral density function will be constant, and we can derive the exact expressions for these spectral moments for m equal to 0, 1, 2, and to a first order approximation we can actually show that rho 0 ij, rho 1 ij and rho 2 ij are given by this these expressions. The exact expressions are much longer than this, there is an approximation here in deriving this. Now, these approximations compare well with exact solutions. I think the error is less than about 1% for frequencies between ratios between 0.8 to 1. Now, we are assuming these expressions are obtained under the assumption that the ground motion is acceleration is modeled as a white noise excitation. We can continue to use these expressions if we make the approximation that the power spectral density function of ground acceleration, which may not be white, correspond to a white noise process, but if it is slowly varying in the neighborhood of system natural frequencies, we can still approximate these moments by using these expressions, and indeed that is the approximation that we are going to make in the subsequent analysis. Now, let us now consider the problem of analyzing the response peaks. Now we bring in the assumption that the excitation process is Gaussian, and I am interested in R tau, which is maximum value of absolute value of R of t over a duration tau, and this tau is the time duration segmented from the steady state. It is not from 0 to t is not from 0 to tau, but it is a segment of length tau in the steady state. We already discussed how to derive the probability distribution of the peaks of this kind, my maximum values of this kind, and I will not repeat that exercise. I will simply recall the expressions, and these expressions are slightly more generalized than the expression that I provided in the discussion in the earlier lectures, but these generalizations I think if you can refer to the papers by Dirk Huygens which I have provided, you will be able to understand what these generalizations are. Now, here we are introducing a variable S, which is the state variable normalized with respect to the stand deviation. So, this is the normalized barrier, and nu is the mean upcrossing rate given in terms of the spectral moments, and this delta E is related to this delta, which is a shape factor that lies between 0 and 1. If delta is 0, the process is narrow banded, and if delta is 1, the process is broad banded. Close to unity means broad banded process. Now, we are interested, for example, in the p expected value of R tau, and we will express this as a factor p into the standard deviation of R tau. So, that I write it as p sigma r, and standard deviation R tau I write it as q into standard deviation of R of t. Sigma r is the standard deviation of process R of t, and this p q are known as peak factors. So, there is information available on how these peak factors behave, and some of these I have provided in the earlier lectures. So, these are slightly more generalized. Peak factor for the mean is given by this, the peak factor for the standard deviation is given by this. For nu tau between 10 to 1000 and delta from 0.11 to 1, and for large nu tau we get this these approximations, which I think was these were what we saw in the previous lectures. Now, till now whatever I have discussed is simply the application of random aberration principle. We are simply recalling what we have studied in some form earlier. Now, let us now consider the problem where the excitation process is described in terms of response spectrum and not the power spectral density function. So, we introduce the notation S tau bar as the mean value of the maximum absolute response of an oscillator over duration tau in the steady state, where omega is the natural frequency of the oscillator and eta is the damping ratio of the oscillator. So, if you recall the definition of response spectrum for relative displacement that we discussed in the previous lecture, it is clear that this quantity S tau bar is nothing, we can interpret it as the response spectrum of excitation f of t. Now, let us now consider how we can apply principles of random aberration analysis if the excitation is specified in terms of this response spectrum. It is not the power spectral density function, but it is a response spectrum. That is how to evaluate the response of a multi-degree freedom system when f of t is specified in terms of this spectrum, which is the response spectrum and not the power spectral density function. Now, we will quickly recall nu I is the mean upcrossing rate in terms of the second and 0th order spectral moments, and this is the shape factor. Now, we will assume that excitation is broadbanded. So, for broadband excitation within the frequency range of interest, the above expressions can be approximated by results for the case of excitation being white noise process. This is the approximation we make, and for once this approximation accepted, we get simplified values for nu I and delta I. Now, if we now use these simplified versions into the formulae for peak factors, we get peak factors for the ith and ith generalized coordinate, where I runs from 1 to n. Now, the definition is expected value of maximum of Si of t over tau, I call it as S tau bar omega comma eta. Now, the moments of the power spectral density function can be derived in terms of the given response spectrum. Recall that Pi is the peak factor, therefore, lambda 0 II, which is nothing but the variance, is this peak value divided by the associated peak factor. This is a square because it is a variance. Similarly, I get lambda 1 II and lambda 2 II in terms of the given quantity S bar of tau and the peak factors Pi. Now, we have already shown these expressions. Now, we are going to utilize them and go back to our expression for the spectral moment, mth order spectral moment for the response process R of t, where there is a summation implied. We were discussing about the spectral moments of the generalized coordinates. Now, we have to go back to the sum. So, lambda m is this and lambda m ij is the mth spectral moment associated with ith and jth generalized coordinates. Now, we can use the formula star and double star to get lambda naught, lambda 1, lambda 2 in terms of response spectrum coordinates. Now, if I denote Ri tau bar as psi I into S bar omega I eta I can show that the standard deviation of the response quantity R is given by this. Pi, Pj are the peak factors for ith and mean of ith and jth generalized coordinates. Sigma R dot similarly I get in terms of this. This rho 0 ij and rho 2 ij, we have now expressions in terms of system natural frequencies and mode shapes, etc., damping, etc. Therefore, once I get the standard deviation of the response quantity R of t, now I will multiply this standard deviation by the peak factor associated with the response quantity R of t. So, if I take this p inside, I get the ratio p square by pi pj rho 0 ij and these quantities. Similarly, the standard deviation of the peak response can be derived. Instead of the peak factor p, we use the peak factor q and we get this formula. These are the formula for the peak factors p and q for the response quantity R of t. Now, quantity of special interest for us is the mean of the peak response. So, that is p into sigma r. Now, it can be verified that the ratio p by pi is approximately equal to 1 over the frequency range of parameter range that we are interested in, and consequently we can approximate this ratio p square divided by pi pj as unity. This is an important assumption in the development of this combination rule that we are discussing. If we accept that, then we have this r bar of tau as rho 0 ij summation over ij rho 0 ij ri tau bar rj tau bar. Now, there are no peak factors that appear in this in these terms. So, we can separate the terms corresponding to I equal to j and I not equal to j. If we write that, the first set of terms is summation over I and r bar square I tau, and the other terms which is the double summation where summation is over I and j such that I is not equal to j. This actually indicates a contribution due to modal interactions. If you ignore modal interaction, this will be our approximation. If you include modal interactions, then we have to combine these two. Now, if we ignore the modal interactions, we get a rule known as square root of sum of squares or known as SRSS rule. So, this is a modal combination rule that we will use. We simply find the maximum of the individual generalized coordinates and square them and add it up, add all of them and take square root. So, this is sum of squares square root of sum of squares method. Now, we can get an improvement to this rule by including the terms which contribute to the modal interaction, and if we do that, then this rule is known as complete quadratic combination rule. So, these two rules are some of the popular modal combination rules that is widely available in softwares. So, the point that you must understand is the genesis of these rules lie in the application of principles of random aberration analysis. Although in a practice one may not model earthquake ground acceleration as a random process and perform a full fledged reliability analysis, but still even for a deterministic analysis, some of the rules that are followed therein have basis in linear random aberration principles. So, that is the point being made here. A few remarks. This SRSS rule can be deemed satisfactory for systems in which the natural frequencies are well separated and modal damping is not very large. And of course, we also want that excitation is broad banded and the strong phase of the ground shaking is long enough, because we are assuming the excitation to be stationary white noise. So, that requires broadband excitations and excitation to be fairly long, so that the stationarity assumption is justified. Since we are ignoring modal interactions, we require that the natural frequencies are well separated and the modal damping is not very large. If modal damping becomes large, that will itself induce interaction between neighboring modes. So, if these conditions are satisfied, SRSS rule provides reasonably good solution. On the other hand, the CQC rule allows for correction due to modal interactions and hence is suited for systems with closely spaced modes. The way we have derived this CQC rule, it can be implemented without having to evaluate the spectral moments. So, that is the advantage of making the simplifications in on the nature of excitation, bandwidth, etc. Now, mean peak response is not dependent explicitly on the period tau. So, that is another feature of applying CQC rule. Some of the assumptions can be recalled again. We are assuming that excitation is taken to be stationary Gaussian white noise. So, the duration of the strong phase motion phase of the earthquake needs to be long and the excitation should be broad banded. The ratio of response peak factor and the modal peak factor is taken to be unity. This also has to be borne in mind. Now, we begin the discussion on the next topic. How are stochastic models arrived for earthquake ground motions? So, I will present a sequence of examples with reasonable increasing level of complexity, so that you get a flavor of how stochastic process theory has been applied in modeling earthquake ground motion. So, we will begin with discussion on single component. We will assume to start with the earthquake ground acceleration is a stationary random process and we will consider the question how to characterize its power spectral density function. Next, we know that earthquake is a transient phenomena, therefore, the use of a stationary model is not entirely satisfactory. So, what is the influence of the transient nature of excitation in arriving at stochastic model for excitation? This non-stationarity, as we will see shortly, can be in terms of amplitude modulation or it could be in the frequency content. the frequency content of earthquake ground acceleration at different times could be different, because the earthquake ground acceleration is a consequence of summation of different kinds of waves, and each of these waves have characteristic properties. Therefore, given that these waves arrive at different times, the ground acceleration will be dominated by different types of wave types at different times, and consequently there will be a non-stationarity in frequency content also. The earthquake ground acceleration at any point is a vector. So, it can be resolved into 3 components of translation and 3 components of rotation. Therefore, if we are interested in characterizing the effect of earthquake ground motion at any point, we need to construct a vector random process model. So, that is the next level of complexity that we can consider. Similarly, as earthquake waves propagate through the earth's crust, the ground acceleration would vary from point to point. It will not be the same at all the points on the earth's crust, and we need to worry about the influence of the spatial variability on the load models, and that takes us to random field models for earthquake ground acceleration. There are 2 approaches to modeling earthquake ground motion. One is assuming that earthquake ground motion is a Gaussian random process. The other alternative is to use what is known as Poisson pulse process models. This we have discussed briefly when we discussed theory of random process. I will return to some of the basic issues during this discussion. So, what are the main concerns in modeling? We would like to capture correctly the frequency content in the ground motion. That depends on actually the local soil conditions. The frequencies typically vary from up to about 30 to 35 hertz, and the next is the transient nature and duration. The earthquake does not last forever, typically 30 second to maybe 120 second one could experience strong ground motion, and this has to be reflected in our model. As I was already mentioning, there is issues about time dependent frequency content that also needs to be included. Then questions about multi-component nature of the ground motions and spatial variability that needs to be considered, and questions on modeling translations as well as rotations. The rotations are not widely discussed, but translations are discussed, and when I talk about translation, we have a model for not only acceleration, but also we need to consider models for associated displacement and velocity components. Now, we should also think of what are the underlying seismological considerations in the arriving at the power spectral density function models. Should we be using a set of instrumental records and then make a model through statistical methods using statistical principles, or should we also include to certain extent the physics of wave propagation from focus to the site. So, some of these issues we will touch upon as we go along. One of the conceptually simple model for earthquake ground acceleration is provided by Kanai and Tajimi. Here we consider the soil layer at a given site, and we assume that at the bedrock level the earthquake induced ground acceleration is a white noise process, and we will model the soil layer as a single degree freedom system, and the absolute response of this mass is taken as the so called free field ground acceleration. So, this is a simple mechanistic model, and it basically takes into account the local site conditions in arriving at the ground acceleration. So, this we have discussed at various points in the course. So, I need not have to get into all the details. So, by applying methods of linear random aberration analysis, we can derive the power spectral density function for the absolute acceleration at the ground surface, and this is the so called Kanai-Tajimi power spectral density model, this one. We also saw that this power spectral density function, this model has certain difficulties as omega becomes small, especially in specifying displacements and velocities. To circumvent that, Clough and Penzin proposed that the ground acceleration be further passed through a high pass filter, and that filter characteristic is shown here. So, the power spectral density thus now becomes gets filtered through another mathematical entity. This is a high pass filter transfer function. So, if you use this model, the ground acceleration schematically looks like this. This is a sample of a stationary random process, and the question is, how do you introduce non-stationarity? Now, non-stationarity, as I was mentioning, there are two issues that we need to consider. One is the non-stationarity in amplitudes, the other one is frequency content. For the time being, if we focus only on amplitude modulation, we can use this strategy where we consider the ground acceleration to be product of E of t into S of t, where E of t is a deterministic envelope function and S of t is a 0 mean stationary Gaussian random process, which could be actually the Kanai-Tajmi or the Clough and Penzin random processes. So, in the literature there are different models have been proposed for this envelope. Some of them are here. This is A naught exponential e raised to minus alpha t minus e raised to minus beta t. This is a combination product of A naught plus A1 of t into exponential minus alpha t. So, there are many more such envelopes in the existing literature. So, they basically capture the non-stationary trend in the earthquake ground motion. So, the one of that typically is shown here. This is E of t and this is S of t into E of t. So, if we generate S of t following say Kanai-Tajmi model or Clough and Penzin model, we will be able to take into account the local soil conditions, and this envelope ensures that we are capturing the transient nature of ground motion. I also discussed an alternate approach to simulate ground displacement, velocity and acceleration. In the model that we discussed so far, if we are using a Fourier series representation to simulate samples of S of t, how to simulate the ground displacement and velocity associated with this model is not very clear. So, what we could do is we start with the equations for the soil medium and the high pass filter and write the time domain equations. So, what we assume is at the bedrock level the excitation is modeled as envelope multiplied by a white noise process. So, in the previous one of the previous lectures we discussed how this set of differential equations can be interpreted as a set of stochastic differential equations and how we could obtain samples using Ito-Taylor expansion based numerical schemes. So, based on that I showed some of the samples. This is a sample of a displacement. We can clearly see there is a non-stationary trend. This is velocity, this is acceleration. So, the envelope here is something like this. Okay. Now, how about the problem of treating non-stationarity in frequency content? So, here we will discuss what are known as random pulse processes, and we will show that such processes have what are known as evolutionary power spectral density function, and they will be successful in capturing non-stationarity in both frequency and amplitude. Now, we need to recall some of the concepts that we discussed when we introduced probability and random processes. There were few things that were postponed during that discussion. Now is the time to return to some of that, and we will quickly see what mathematical tools we need to analyze a random pulse process. So, the concept of characteristic function and characteristic functional is central to this discussion. So, we will quickly recall these notions. So, let x be a random variable and we define the characteristic function as the expected value of e raised to I theta x, and this is this expectation. Now, if we expand I theta x in series, we can show that this mx of theta is related to the moments of the random variable x, and using, if we are given this characteristic function, we can evaluate the moments using this formula. So, they are also called moment generating functions. So, for example, if x is a Gaussian random variable with mean m and standard deviation sigma, we have shown that the characteristic function is given by this, and we also define what is known as log characteristic function, which is logarithm of the characteristic function, and this is written in this form, and for a Gaussian random variable the log characteristic function is defined through this expression. Now, if we write the log characteristic function for a general random variable, this will write it as kappa n of x. This kappa n of x, which are the terms appearing in this kind of representation for the log characteristic function, are known as cumulants. Now, we will see more on this shortly, but we will now generalize the notion of characteristic function and the log characteristic function for a set of random variables. Suppose if I consider m random variables x1, x2, xm, then the mth order joint characteristic function is defined as the expectation of e raised to I summation theta n xn. So, this can be expressed in terms of a multidimensional integral expectation of this quantity. So, this is a m dimensional joint characteristic function. Now, if we are given m dimensional characteristic function, we can evaluate moments of this kind in terms of the joint characteristic function using this formula. This also can be proved easily by if we expand e raised to these terms inside the parenthesis in a series and use the relations as shown here, we will get the required moments. Now, we can following this we can write the joint characteristic function in terms of the moments. So, this will include first order, second order and mth order joint moments of all these random variables, and it is a series. Now, if I take the logarithm of this, I get the log characteristic function, and this can be written in yet another series where these kappas are the cumulants, and a cumulant of the order m1 plus m2 plus so on and so forth mm is given through this relation, and we can show that the first cumulant is the mean value and the second order joint cumulant is actually the covariance, and we can derive the higher order cumulants which will be related to the moments of this random variables x2, x1, but these relations are more complicated. But for a Gaussian set of Gaussian random variables, it can be shown that all cumulants of order greater than or 3 are equal to 0, and the first cumulant is the mean and second cumulant is the covariance. Now, how do we generalize the notion of a characteristic function to a random process? Suppose x of t is a random process and we define what is known as characteristic functional, where denoted by mx of theta of t, which is actually the expected value of integral I theta of t x of t dt. Now, of course, if I take theta of t to be a sum of Dirac delta functions, we will get the joint characteristic function of the m random variables stationed at t equal to t1, t2, t3, tm. But I am not interested in this, I am interested in a general form of the characteristic function, that is called characteristic functional. So, here again I can expand this e raised to this quantity in a series, and we get these expressions, and we can take logarithm of this. This will help us to define the first cumulant and second cumulant and so on and so forth. For a Gaussian random process, we can show that the characteristic function is given in terms of the mean and the covariance function, and this is the characteristic functional. The logarithm of this is again expressed in terms of the mean and the covariance function. This can be verified. This is conceptually simple, but somewhat tedious to write down. Now, we will now consider a random process x of t, we call it as Poisson pulse process, where the summation is from k equal to 1 to n of t of certain pulses w k t comma tau k, where n of t is a Poisson counting process. W k t comma tau k is a random pulse commencing at time tau k. Tau k are random point distributed uniformly in 0 to t. That means, we have a time axis say 0 to capital T, and suppose there are say some randomly placed points. We assume that the process x of t is a consequence of a pulse that arrives at, say, this is tau 1, this is tau 2, this is tau 3. The pulse arrived at tau 1 is, this is my W1. the pulse arriving at tau 2 is another random process, tau 2, tau 3 is another pulse. So, at any time t there will be the x of t that we see will be the sum of the effects due to the various pulses that have arrived up to this point. Now, wk t comma tau k is a random pulse commencing at time tau k. Now, a simplified version of that would be, we can assume that the shape of these pulses are identical, but their amplitude is modulated by a random variable yk, the shape is the same and the arrival times are still random. So, in that case yk is the random amplitude of the kth pulse and yk we take to be IID, a set of IID random variables, and w of t comma tau k is a deterministic pulse commencing at t equal to tau k, such that w of t comma tau k is 0 for t less than tau k. That means, till the time tau k is arrived at, this w is 0. Now, with this description I am now interested in characterizing the random process x of t. How do we do that? Suppose I look at the characteristic functional. This is expected value of integral 0 to t theta of t x of t dt. So, for x of t I write now this expression and I am taking expectation. What I will do is, first I will condition on n of t being equal to n and then multiply by the probability of n of t equal to n, and take this mx of theta as a double expectation. So, if we do that, first the conditional expectation can be evaluated and it can be summed later over these probabilities, and this is what we get here. So, the probability of n of t equal to n and expected value of this quantity where this n of t is conditioned at n. Now, for probability of n of t equal to n, I can write now the Poisson model for that. We get this expression as shown here, and we introduce a notation alpha, where alpha is this particular quantity. So, p of, in this study, p of n of t equal to n, we are assuming the arrival rate to be and integral lambda of tau d tau 0 to t to the power of k by k factorial. So, this is the model that we are assuming for Poisson model with a time dependent arrival rate. Now, this alpha is given by here and this can be simplified. This is an expectation. Now, what is random here are the random variable y and this tau k, and if we interpret them carefully and allow for the fact that yks are IID and tau k's are Poisson points, we get this expression. So, we will return to the definition of mx of theta of t. This is probability of n of t equal to n into 1 plus alpha to the power of n. So, now n of t equal to n is nothing but this exponential minus 0 to t lambda of tau d tau 1 by n factorial and 0 to t lambda tau d tau, this is like e raised to minus a to the power of k by k factorial into 1 plus alpha to the power of n. So, we can rearrange these terms a bit. This term is independent of n, the first term that is taken out, and we take this 1 plus alpha inside this, because there is a power n that is common to both these expressions, and if you simplify, we can show that the log characteristic function is given by this and the characteristic function is this. So, the log characteristic function is alpha into 0 to t lambda of tau d tau. Now, we are interested in finding the cumulants. So, we look at this log characteristic functional a bit more carefully, and we substitute for the expression for alpha in this, and if we compare this with the series expansion for the log characteristic function, we will be able to identify the first and second order cumulants, and you can show that the mth order cumulant is given in terms of the random variable y and these pulses in this form. Now, the integral upper limit is minimum of T1 comma T2 comma Tm, simply because of this definition you can verify that it is indeed true. And from this, now if we look at the mean, the first cumulant, it will be given by this, and the second cumulant is given by this, and from this if we now consider second cumulant is nothing but the covariance. So, if you, from this we can compute the variance and we get in this form. If we take the special case of W of t comma tau to be a function of time difference tau, these simplifications and arrival rate to be constant, the formulary leads to certain simplifications. I leave this as an exercise. You can show that these simplified results are obtained under these assumptions. There is yet another concept that we need to discuss before we consider modeling the non-stationarity in frequency content in ground accelerations, that is the notion of evolutionary random process. So, I will begin by offering an intuitive explanation for this. So, let us consider a set of random processes xi of t, say I from 1 to n, that is x1, x2, x3, xn. Let us take that each of these random processes have 0 mean and they are stationary, and the power spectral density function is Si of omega for xi of t. Now, let us consider a time interval 0 to t and divide into n segments. Now, I will define a random process x of t as x of t is equal to x1 of t if t is between 0 to t1, otherwise x2 of t it is between t1 to t2 and so on and so forth. So, x of t is defined in terms of capital N number of segments, where each segment is one random process x1 of t. Since properties of x1, x2, x3, xn are all different, it is clear that x of t is a non-stationary random process. Now, if we look at the power spectral density function, since x of t is equal to x1 of t over this duration, I can notionally say that the power spectral density function of x of t, if you are interested in the time duration 0 to t1, will be s1 of omega, and if you are interested in t1 to t2, it is s2 of omega, and so on and so forth. So, I can say that the power spectral density function is a time dependent function. This is equal to s1 if t is between 0 to t1, if it is s2 if it is t between t1 to t2, and so on and so forth. Such a process we call it as a evolutionary random process. We can generalize the notion of this evolutionary random process where the number of segments becomes very large and we need to develop certain alternative formulations. So, we consider now the representation kind of a Fourier representation, but in terms of Riemann-Stieltjes integral, we consider x of t to be a of t comma omega exponential I omega t dz of omega. This a of t comma omega is a deterministic function, it is in general complex valued, and z of omega is a orthogonal increment random process, it could be complex valued with expected value of dz of omega is 0 and dz of omega 1 into dz star of omega 2 is Dirac delta of omega 1 minus omega 2. So, here we can write this as omega 1 comma omega 2. Now, what is the mean of x of t? If you follow this, mean of x of t is 0 because mean of this increment is 0, and if you now consider the covariance x of t1 into x star of t2, I am assuming that x of t in general is complex valued, we can write this in terms of this, we get this expression, and if we now write for this quantity the Dirac delta function and d psi of omega 1 comma omega 2, we get this simplified expression because there is a Dirac delta function, one of the integration can be done easily. Now, if t1 equal to t2, I get the variance and I get this expression. Now, if this capital psi of omega is a differentiable function, then the above this integral can be taken as a Riemann integral, and I can write this as d psi of omega can be written as phi of omega into d omega. If I do this, we get this expression, and now phi of omega, so for example, if a is not a function of time, phi of omega is nothing but the power spectral density function. Now, we interpret this function modulus of a of t comma omega whole square into phi of omega as the non-stationary or the evolutionary power spectral density function of x of t. Now, we have already seen random process models where x of t is obtained as E of t into y of t, where E of t is deterministic and y of t is a 0 means stationary random process. If we now use this concept here, we get sigma x square of t is E square of t minus infinity to infinity sy of omega d omega. If E square of t is unity, it is independent of time, then of course we recover the stationary random process. In this case, where E of t is a function of time, we call x of t to be uniformly modulated non-stationary random process. Here the non-stationarity is in non-stationary feature that we are capturing is the amplitude modulation in x of t, but not the frequency variation. So, you want to capture the time varying nature of frequency content, we have to use this kind of models. These are evolutionary power spectral density function models. I will show in the next lecture that the Poisson pulse process, if you look at its power spectral density function, it has an evolutionary, it is actually a evolutionary power spectral density model. So, that I will show in due course. Now, equipped with these basic mathematical tools, now we will return to the problem of modeling earthquake ground motions, and we propose that the earthquake ground motion be modeled as a filtered Poisson process, that is a Poisson pulse process that we were discussing just now. The rationale here is that during earthquakes, slips occur along fault lines in an intermittent manner. This sends out a train of stress waves in the earth crust, and these at any given point on the crust, these waves arrive as and how the slipping process proceeds, these waves arrive at different times. This superposition of different waves results in the ground shaking. So, now we can propose a model therefore, that x of t, which is the ground motion observed at a given site, is superposition of several stress waves with random amplitudes arriving at random time instants, and the number of stress waves that arrive is modeled as a Poisson counting process. So, n of t is the counting process, it is Poisson, and arrival rate for purpose of discussion we take it to be function of time. Tau j are the arrival times which are again random. We take this pulse w t comma tau j deterministic pulse shape for it is equal to 0 for t less than or equal to tau j. Yj is the random magnitude of jth pulse, and typically we take Yj to be a sequence of IIDs. We have shown now through the use of characteristic functionals what is the mean and what is the covariance of this pulse process. So, this is the expression for the variance. Now, as I said, I will be showing shortly that this process actually captures the not only captures the modulation non-stationarity in amplitude modulation, but also the time varying nature of the frequency content. Now, the question is how do you select this pulse shape? So, what we could do is we can use different models. I will discuss one of the models in today's lecture, and other models will take up in the next lecture. So, what we will do is we will assume that the pulses are outputs of a Kanai-Tajimi single degree freedom model. That means, as in Kanai-Tajimi model, the soil layer is modeled as an elastic half space which can be represented as single degree freedom system. So, the Gowning equation for the transmission of a single pulse is given through this, and the transfer function is h1 of omega, and the Fourier transform of this will give me the impulse h1 of t, and I will assume that the pulse shape w is actually this impulse response. That means, what I am assuming is at the bedrock level I apply a unit impulse, and whatever I see here as the acceleration I will take that as a pulse, and this will convolve with whatever waves that are arriving there, and we will get the ground motions through this model. So, in this case the ground motion g of t is given as j equal to 1 to n of t yj h1 t comma tau j. Now, we can improve upon this and we will consider some of these improvements in the next lecture. So, at this stage we will conclude the present lecture.